All right, we are back with the Xanadu Quantum Codebook. I have a lot of ideas for, I think, some very exciting content and projects and results to share, but it takes a lot of work to do all of that. And these videos where I work on the codebook take effectively no work, or if it's a 20-minute video, it takes exactly 20 minutes of work. So they're pretty trivial to sort of produce, which is why they sort of been inundated my channel recently. Simply because they're so much easier, and additionally because they seem to be quite popular. Not that that's something I consider when doing things. I just do whatever I want to do, but I do notice that the codebook walkthrough has been very popular, which is on a personal level is kind of surprising because it doesn't, I don't know, it doesn't seem to be, I don't know, it's just surprising to me, but I guess that's somewhat irrelevant. And so, yeah, we'll just get right into it. And if you remember last time, before we finished up the whole introductory chapter, which took a while, took like 5 separate discussions, but then we were able to do the next step, the A section, all in one go. So let's see if we can do the same with the Grover section, section G here. There's only 5, so who knows? I've done a fair amount of work with Grovers. There's a nice video I already have made about it in the past that you can find from 7 months ago. Wow, 7 months ago. So long ago. Making me feel old right now, seeing how time passes. That's a real existential shock. Anyway, for now, we're just going to be going through the code as always, and who knows, maybe we'll reach a point where I need to actually read this right section, but for now I can just flex, I guess, my knowledge of basic quantum computing and not really pay too much attention to this right section. It's probably worth going through all the answers, right? There's like exercises, but I mean, that's probably worth doing if there's any, maybe I'll do that sometime. I think they have an answer key for all of them, so I don't think they show all their work, so I don't really see that much point in doing that. Whereas here, there's no work. All right. That was a long introduction. We'll get into it now. So once again, we have the oracle that, what am I doing here? Complete the following code for returning the amplitudes after the oracle. The oracle is accessible as oracle matrix, where combo is a secret combination. Okay, so we want to apply Adamar gates. I wonder if I can do I don't know. I'll just do it this way. Now we apply the oracle. And I actually remember this time to cast it to a qubit unitary of oracle matrix combo wires equals 5, 1, and bits. Then we want the exact same process. Oh wait, the after applying the okay, we don't want to do anything afterwards. So you can see the oracle has flipped the amplitude of this given state, which is exactly what the Grover's oracle does. All right. Now we need a new oracle, and this is the diffusion operator, and this is what I covered extensively before. So now we can define the operator as a matrix and visualize. Oh, fine. Okay. So we want to do I equals pi dot of 2 to the bits. Might as well be general here. And then we want, I'll do the other one. So phi equals p equals 1 over the square root of, let's see, this is the even superposition, square root of n, right? Because you're squaring it. I think there's 2, if there's 4, the square root of n, of 4 states, square root of 2 to the n. It's because they're equally distributed, right? So if you have 2 bits, 1 qubit. If you have 2 qubits, there's 4 states. If you have 3 qubits, there's 9 states. So it would be 1 over square root of 9, which is 1/3. Okay, yeah. Then we want our array that is simply 1. Or I guess there's 1s, right? Equals 2 to the n bits. And then we want to say, okay, return. I don't need this. So we want to return as defined 2 pi dot order e minus I. Let's hope that's right. Now we want to say apply the oracle and diffusion matrix to the uniform superposition. So I'm going to go up here, copy all that code. Why did it not copy? Then I'm going to do this. Now we have our diffusion operator. So we want to do diffusion matrix. This is actually like exactly what I did in that other Grover's video. And we can see, wow, it'll flip it around the mean, because that's what Grover's average is all about. I don't have it over here, the Grover's algorithm. So now this is much more likely, right, for combo 0, 0, 0. And now complete the code below and verify I have 2 Grovers. Here's something interesting, actually, is that for multiple Grover's iterations, there is actually a point of, why does it not copy? Okay, there's a point of diminishing returns. Like, you're supposed to do Grover's iteration for the floor of square root of n iterations. And if you do it for more than that, it can actually decrease the efficacy. That was something I remember when I took a class in this that surprised, I found it out experimentally and surprised us sort of theoretically. Never really thought about it before. But basically, if this gets really big, right? Let's suppose this is very nearly 1, or suppose it is 1 even, and you flip it out and then, or very nearly when you flip it down, right? And then you say, okay, I'm subtracting the mean from everything. Well, the mean is actually going to be negative, right? If the mean is negative, so if this has more weight than all of these, the mean will be negative when you flip it. And then these will actually increase and this will decrease. So that's just a fun little thing, I guess. Might be trivial to some people, but that was not trivial to me. There we go, easy peasy. All right. Oh, would you look at that? This is actually what they're going to talk about. Wow. That's fun. Hey, look, they did it like the same way that I did. That's very cool. Yeah, I'm gonna go back and copy my code because I don't feel like rewriting things. I'll try to copy it this time. Oh, I forgot to, I don't know if it would actually be just faster to type it, but I don't feel like typing it. And then I want to say steps. We can do tab, and then I think that's all we needed to do. Unexpected indent. Oh, there we go. Oh, how many steps are we supposed to do? Oh, we'll do 10. Why not? What is going on here? What am I supposed to be looking at in that plot? I really don't understand what this plot is showing. Oh, that's what this plot. Why is it not just showing the probability? Why is it doing it this way? Searching. They always do just geometry explanation. Whenever I learned about Grover's algorithm, I never actually found it useful to see this geometry, but maybe that's just me. All right, sure. We know the answer is 5. So what do you mean it's not right? Oh, do we have to actually go up? Okay. 1, 2. You can see a little thing going up. 3, 4. Okay, 4. Okay, wait a minute. Oh, we're supposed to determine the optimal, not that the optimal number is equal to n equal to 5. What is n here? What am I even? Oh, n bits. Oh, okay. Ah, well, that was quick. All right. Arbitrary matrices are hard to build. This is definitely true. Okay, so we're going to use the combo and do dot multi-controlled x. Control wires are the let's see, in bits. Is this gonna work? Let's see. What does it have to be? I think it has to be query register control wires. Single target given by wires. We have aux, and then we have combo. Oh, we have to do, wow, throwback to computer science 1 when I learned how to program in Python and had to do lots of string manipulation, so I remember how to do it. Of course, oh, but I actually do. Well, whatever. I think that should be right. Wrong number of 3 expected. What do you mean? Wrong number of 3 parameters past 0 expected? What do you mean 0? Oh, and it converted us. Hey, what do you know? That's exactly what I did. That's hilarious. I did not even see that. But, okay, I don't understand why it says that. Did I mistype this? No. Oh, what? How is this wrong? Oh, do I have to actually? Oh, why do I have to actually say control wires equals wires? Why do I have to do this? Control values equal. This better not work. And it works. Oh, that's annoying. Implement the diffusion operator in terms of the multi-controlled X. Okay, that's handy. I'm going to copy this again. Show you the. Okay, so the first thing to do is to do add another transform on query register. We're going to do that twice, actually. Once before, once after, and then it's going to be controlled. This is all the same. But then this is not combo string. It is 0 times length of query register. Oh, oopsies. Query. Okay, so the first thing we want to do is add another transform. First thing we're going to do is kill poly x wires equals auxiliary. Then we're going to say Adamar transform all wires, which is wires. Then we're going to say Oracle combo. Then we're going to say diffusion. Would you look at that? Wow. What's the time at? 17 minutes. All right. All right. What are we looking at here? The speed up, a quadratic speed up, which is why we can't. A lot of people, when they see Grovers, are like, "Oh, OMG, we can solve the SAT problem, right?" Because the logic of 3 SAT maps somewhat trivially onto the Grover's algorithm. In fact, I think it's in the Qiskit textbook. Why is LinkedIn coming up? Yeah, you can see here, which is certainly fine, but there's no like NP guaranteed speed up because this is just a quadratic speed up of an exponential algorithm. Anyway, what am I doing here? Implement the Grover circuit. Didn't I just do that? Can I just copy this again? Oh, oopsies. Diffusion takes positional arguments using end bits. Well, then I'll pass it in bits. Maybe I should do it. All wires. Okay, how did they implement their diffusion? I need to go back. What is diffusion even doing? Okay. Maybe I need to look at how they do diffusion. Okay, let's see. The secret combination represented as a list, number of steps, sure. Probability, sure. No problemo. All right. This all seems fine. Why is this not right? Length of combo. Yeah, so there's only that many wires, but why is it not giving the right answer? Oh. Oh, okay. That's because we don't need this. Oh, we do? But we're measuring the query register, not the... I don't know what is going on, and I don't want to read this. Okay, what is going on? Okay, I'll read it. Since we know local peak, yada yada yada, problems sinusoidally, complete the function below. The Oracle Hadamard transform and I don't understand how this is wrong. They don't tell me what diffusion is since it's different than what we previously defined diffusion as. It says over here, no. Okay, what is going on here? Like, I don't know if this is, you don't need an auxiliary qubit, right? You saw back here. Right, yeah. There was no auxiliary qubit right here. We just measured the most likely state. But then they have an auxiliary qubit here, so I assume that one exists. And so we're doing this diffusion operator on, I don't understand. How this is wrong. The Oracle Hadamard transformation diffusion operator. Note that the inner. Okay, yeah, sure. It seems like literally the same problem as before. Implement the Grover circuit. PolyX Hadamard Oracle diffusion. Let's see how this is different at the end of this. PolyX Hadamard diffusion. Oracle diffusion. Let me look at what my diffusion did. Yeah, it seems like the same thing. How is this not working? Okay, let's see. I wonder who at Xanadu is just an insane fan of the Beatles. I don't know. I'm looking at this is not relevant at all. I just saw them and I'm like, I wonder who is just a fan of the Beatles because these are really not the best Beatles songs. But that's okay. Let's see. Where's their code book? Here it is. I do not need passwords. I never use Edge outside of this, so it doesn't matter to me. Codebook. All right, what are we looking at? G4.1. HHIH. What is this? It's not the right one. That's not the right one. Oh, I remember struggling with that one though. All right. No, this one doesn't work because they didn't apply. Oh, why doesn't that one work? Oh, it's because they didn't say polyx. Maybe that's what they want me to do though. They want me to orient this differently. I should give the exact same answers now, but I'll try it this way. Yeah, it's the same circuit, so let's see. Okay. I'm gonna automate this, minor algebra, make music, pair programming, all about qubits measurement. Very unfortunate. Why is this wrong? Okay, I need to read this closely. There's probably something trivial I'm missing here. Okay, so let's see. All right, focus hard. Hadamard transform. Okay, that's clear. Diffusion. Sure, that's clear. Oh my god, am I just blind? I am actually just blind. I'm pretty sure this is... Invalid syntax, line 25. Oh my gosh, okay. Yeah, I'm very... Sometimes it helps to read, but that's okay. I still believe we can finish this out strong. Append the, let's see, Grover iter combo. Iter combo. Hi. Oh, we don't even have to do that. That's fine. Jeez. Oh, we do have to do that. No, I see. I have to actually read the problem. Okay, so we're going to keep track of all of the results. And then we're going to say opt steps append argmin is +3. There we go. It is not right. Maybe I will print. What am I actually printing? Oh, that's why. What I really want to do is append the 0th. I need to actually get the right probability. Okay, I really do not like this format, so I'm going to cast them. Oopsies. All right, now let's see. We do not need to do that. That's the problem. We actually have to do +1 instead of +3. The +3 was because I was confusing myself. But the +1 is because they're offset by index 1. Oh, and also because I don't know how this works, I guess. I want argmax. Wow, this is a poor problem for me. And that's also wrong. Let me see. What am I missing here? All right, let's actually think. I'm trying to speed run these, so it's all right. For n and 3, 4, 5, 6, determine the optimal number of steps. As usual, we choose a simple combination. Since the optimal number of steps is not dependent, use function local. Oh, okay. I will do just that. That is why I'm very silly. Local max or list. Well, it's actually. Hey, what do you know? Okay, this is taking me way longer than it needs to because I'm not actually reading anything. Oh, oopsies. What am I supposed to do here? Am I supposed to be doing this? Oh, I see. Okay, wait, I need to actually look at this. With our answers stored in off steps, we can plot them logarithmically. Oh. Yeah, okay. What is the intercept? 0.79. Not really. I'm kind of skimming this, I admit. Oh, the intercept is negative 0. Okay, this is really, I really need to read. Okay, I promise. This one I'm going to read on. Multiple solutions. I'm going to read here. Create an oracle for a random set of solutions of a given size using the multi-controlled X gate. Remember that this takes a string rather than a list. All right. QML.multi-controlled X. Let me go get this stupid terminology from a previous setup. All right. And we say, okay, the control wire is query. All right. Below, we provided the routine for regular Go research, except the oracle is using the oracle from the previous. Well, all we have to do then is specify. What is it called? Oracle multi. And bits. So what I want to specify? Oh, combos is actually. Combos. All right. For n equals 5, m is 2, 4, sorry, 1, 2, 4. Determine the optimal number of steps. Once again, the optimal number of steps does not depend. All right, so we're going to do the same process here. We're going to say, let's look at this one over here. We're going to say, oh, whoopsies, it's actually Grover error multi. There we go. Same sort of idea that we're just repeating over them. You can work out, once again, it's pi over 4 times square root of n, but this time it's over m. And now I'm going to read this time and see, once again, the plotting is still 0.5. And the intercept this time is let's see. Intercept is 2.03. All right, so as the number of bits increases, it makes sense that the number of steps you would need to do would decrease because you have more chance, right? Just even a brute force algorithm, the more solutions you have, the more easy it is to guess them. Oh, we're done. All right, now we just have one more module that we will do next time.